this stuff of fantasizing and looking at the world, imagining things, which really isn't fantasizing because you're only trying to imagine the way it really is, comes in handy sometimes. The other day I was at the dentist and he's getting ready with his electric drill to make holes. And I thought I better think of something fast or else it's going to hurt. And then I thought about this little motor going around and what was it that made it turn? And what was going on? And what's going on is there's a dam some distance away here, and water going over the dam turns a great big wheel, right? And this wheel is connected with long, thin pieces of copper, which split up into other pieces of copper and split up and spread all over the city. And then they're connected back through another little gadget that makes wheels turn. All the wheels of the city are turning because this thing turns. If this thing stops, all the wheels stop. It starts again, they all start again. And I think that's kind of a marvelous thing of nature. It's extremely curious. That phenomenon I like to think about a lot because all it is copper and iron. See, sometimes we think it's a man-made generator, it's very complicated, the phenomenon is a result of some special something that we made. But it's nature doing it, and it's just iron and copper. And if you took a big long loop of copper and had iron at each end and moved a piece of iron here, the other iron moves at the other piece. And if you get it down to the nothing, just moving a piece of iron in a loop of copper and seeing another piece of iron move, you realize what a fantastic mystery nature is. And you don't even need the iron. You could, if you at least get this pump primed and started, by jiggling copper strands around fast enough, knotting them and unknotting them and so forth, you can get other copper strands to move at the other end of a long connection. And what is it? It's only copper and motion. And we're so used to circumstances in which these electrical phenomena are all canceled out. Everything's sort of neutral, with pushing and pulling. It's really very dull. But nature has these wonderful things, magnetic forces and electrical forces. You comb your hair with your comb and you get some strange condition. So you put it in front of a piece of paper and it lifts up the paper, or the paper jiggles at a distance far away. And that's, in fact, turns out that is the thing that's more deeper inside of everything than the things we're used to. We're used to forces that only act directly, right? You push with your finger, it only acts directly. But then you have to imagine what it is that's pushing with the finger. Here's this little finger's made out of little balls and atoms. And it's got another bunch of atoms that I'm pushing. And there's a little space between those atoms. And this pushing is going through that space. And the only thing that happens with the comb and the paper is that circumstances have arisen which make it possible to see that these forces go through a bigger distance than just the short distance between the atoms. What it is if you have charges like electrons that are both the same. They repel each other with a force. They're little tiny particles. They're a piece of the atom, and they repel each other with a force which is enormous. It's inversely as the square of the distance, just like gravity is inversely as the square of the distance, but gravity is attractive, and this is repulsive. And for two electrons, the gravity is so weak compared to the electricity. Electricity is so much more enormous than the gravity. I can't express it because I don't know the name of the number. It's 1 with 30 or 8 or 40 zeros after the 1. Bigger is electricity. It's so enormous that if I were all electrons, well, the numbers are too big. So if there's also, however, for electrical things, other kind of charge, positive charges. An example of protons are positive. They're inside the nucleus of the atom, and they attract electrons. Opposite charges attract, and like charges repel. So you have to imagine enormous forces where likes are trying to get away from likes, and unlikes are trying to get near the opposite. What would happen if you had a lot of them? All the likes would collect with unlikes. They attract each other. And they get an intimate mixture of pluses and minuses all on top of each other, very close together. You wouldn't have a lot of pluses anywhere because they repel each other. They'll all be compensated by minuses very close. And you get these little knots of plus and minus. The reason that the knots don't get smaller and smaller is because they are particles, and there's quantum mechanical effects that we won't discuss that makes it that you can't get any smaller than a certain size. And so you get these little lumps, which are balls. They're the atoms. The atoms have positive and negative charge, and they're neutralized. They cancel their charge as nearly as they can. And because of this force is so big, it ends up nowhere, with very little left. Because it's so big, it cancels out. There's always so exactly the same pluses and minuses in any normal material. When you comb your hair, it rubs just a little bit extra, or just a few extra minuses, say, here, and somewhere else a few extra pluses. But the forces are so big, there's just the extra ones, which make a force that we can see that seems to be at a long range. And that we find mysterious, and that we need an explanation for. And we try to find an explanation for it in terms of ideas like the forces that are inside of rubber bands or steel bars or twisted things. We would like to have some kind of puller at a distance because we're used to it, that we don't get any push until we're touching. But the fact is that the reason we don't get any push until we're touching is it's the same force as you see at a long distance, only it's come down to short because the pluses and minuses have canceled out so well that you don't feel anything until it gets very, very close. When it gets close enough, of course, it makes a difference which is plus and which is minus and where they are, and they repel each other. So it's kind of fun to imagine this intimate mixture of highly attractive opposites, which are so strong that they cancel out the effects. And it's only sometimes, when you have an excess of one kind and another, that you get this mysterious electrical force. And how can I explain a mysterious electrical force in any other way? Why should I try to explain it in terms of of something like jelly or other things which are made, and I understand, the other way around in terms of strong long-distance forces which have all canceled out. So it's the electrical forces, in fact, and the magnetic forces, in fact, that we have to accept as the base reality in which we're going to explain all the other things. So again, it turns out it's hard to understand. You have to do a lot of imagining. That the real world has as its base a force which acts at a long distance. That we haven't got much experience with that force. We have a peculiar phenomena here and there, but ordinarily we don't have much experience with that force, is simply because that's what requires explanation. That's what requires imagination. The long-distance force we have no other picture for. And in the example of the generator, for instance, what happens is that the electrons, which are a part of an atom, they're pushed by the motion of the copper wires. And it's wonderful to think that you push a few here, and they get too close together, so they push the others because they repel at a long distance. So it's not just like water, which repels at a short distance, but it's a wonderful fluid which repels at a long distance, and the effects therefore can go very quickly through the wire. If there's a little concentration, you go zing through the wire all over the city at once. And you can use that stuff to make signals. You can push a few electrons here and there by talking in a telephone. At the other end of the line, a long line of copper across the city, the electrons respond because of this very rapid interactions over these long distances to what you're saying in this room. And if they've discovered experimentally the existence of these long forces and these rapid motion actions and so forth was a tremendous thing for human beings. I think that the discovery of electricity and magnetism and the electromagnetic effects, which were finally worked out, the full equations for everything was worked out by Maxwell in 1873, is probably the most fundamental transformation of the most remarkable thing in history, the biggest change in history. You can use that stuff to make signals. You can push a few electrons here and there by talking in a telephone. At the other end of the line, a long line of copper across the city, the electrons respond because of this very rapid interactions over these long distances to what you're saying in this room. And if they've discovered experimentally the existence of these long forces and these rapid motion actions and so forth was a tremendous thing for human beings. I think that the discovery of electricity and magnetism and the electromagnetic effects, which were finally worked out, the full equations for everything was worked out by Maxwell in 1873, is probably the most fundamental transformation of the most remarkable thing in history, the biggest change in history.